All right, guys, so let's get started over here. So let me line up this, if I can do something better. All right, so this should be page 109. ES205. Today is April 17, 2018. So you have a homework due today. So do you have questions about the homework?
I have 57.
Which one you want to do? Let me first look at those problems. I printed the solution so I can look at the type of problem it is. I don't want to waste time on a problem that I don't think is good or exam type, no? So which one you say?
Chapter 6, number 57.
Okay. 657. So let's see what that is. Let me just look at the solution kind of quick. $57?
Yeah.
Okay, looks pretty long. Let's see on this one.
You have like electricity.
Yeah, that's fine. Not a big deal. Oh. Yeah, forget about this one. It's not that much for the concept. It's good, but it's just because I saw one equation, which is this one over here. I'll show you that we haven't done. So basically, is that what is the power of a shaft? This is from structure is equal to that weird letter there. I'm guessing is a T for the torque. So the power created by a shaft, rotating shaft, is equal to the torque times the angular velocity of the shaft. Okay? So I don't think that's important for us for this class. So yeah, remove 657. I will probably remove it from the homework.
Number 50 though.
So 57 out then, no? 657 out, if you want, okay? I don't like it. 650. What is 650? Doesn't look like I have it.
It says it gives you a piston and piston assembly with air, and then it gives you two different scenarios for the state.
Two different scenarios of what?
A state 1 and state 2, and then it asks you to determine if it's
650. Okay, I don't have it here, so I missed that one. 50 or 60? So 650. Okay, I mean, let me look at, oh, here it is. Let me see what that is. I guess that one looks okay, just by looking at the solution. So we can do that one. All right, let's do that one. So let's see what 650 is. So I start from 0. So all right, so 650 is right here. Okay, so let's look at this problem. So 650. So air as an ideal gas contained within a piston cylinder assembly. So piston cylinder assembly, air ideal gas, PV equal RT. I don't know if I'm going to need all that stuff, but I just write it down. Is compressed between two specified states. In each of the following cases, can the process occur adiabatically? If yes, determine the work in appropriate units for an adiabatic process between those two states. If no, determine the direction of the heat transfer. Okay, so let's do so let's say case 1. We have P1 equal to 0.1 megapascals. T1 equal to 27 degrees Celsius. P2 is equal to 0.5 megapascals. And T2 is equal to 207 degrees Celsius. And they even tell you to use table 822. So let's see table 822. Okay, so they said to use table 822, so let me see what table 822 is. Okay, so 22. Oh, no. Okay. So, all right. So we have this S upper index O over there. All right. So before we even touch to this, then I should have put. So this is 1013. Does anyone remember the page from the other one? No.
What are you looking for? To change the problem?
Yeah.
It's page 350.
350?
Yeah, you're almost there.
Yeah, so let me stay there then. I was logged over here, so okay, so there we go. So if you guys remember, I think this is the equation that so let's see, last class notes. I think we did it last class. Well, I had the impression we did it last time. Okay. Let me pull this. I thought we did it. I don't see it here, but I'm pretty sure we did it. Okay, so last time we started to work in all this stuff, these TDS relations. And basically we say that, all right, what is the meaning of this relation over here? Yeah, sorry for that. So basically, guys, we were working on this and think, so what happened with this? If this is an ideal substance, if this is constant, we say we could move the CP outside, no? Okay? And I think we were able to rewrite the expression under this form. Okay? But for some gases, we didn't do it. Okay, so let's do that then maybe first. One oh five, 106. So that's where we stopped last time. All right, so let me do one thing before we start this problem then, okay? All right, so page 109. Sorry for that, guys, but I thought we did it, so let's see. So recalling the TDS relations, we had one that was delta S. The change was equal to CV log T2 over T1 plus R log V2 over V1, and the other one was CP log T2 over T1 minus log P1 over P2. Okay. So let's say for an incompressible substance. Do you have an example? Do you know any incompressible substance? Didn't we do this? So I don't have it on notes. Okay, so so then I thought we did this.
Yeah, we did it.
We did, no?
Yeah.
Yeah, so we say, so let's do this very quick and you let me know. I don't find it here on the notes though, so maybe I forgot to put them. Yeah, P2 over P1. Hold on one second. But let me see if I can find this 17108.
I think we did it on.
It was before we did the two problems about the alpha and
Oh, so what was the page? Okay, we did it. I know I was going to lose something. I don't find it now. I'll try to find them later, okay? So anyway, I'll go through this very quick then, okay? That was like a quick review. That should not matter. So for an incompressible substance, what do you know? V1 equals V2. So you're going to have log V2 over V1 equal to 0. So we end up having delta S is basically equal to log to CV log T2 over T1. All right? So if I did it, it's good. Just a review. Then we say, I don't know if I say that, but let's say for air. Let me just say for air, okay? For air, what's going to happen? The term over here, Cp dt over T, Cp is not constant, but Cp will be in function of the temperature. Okay? So we say that, I don't know, is that what I did or no?
Yeah.
So this term over here, Cp over dt, basically will be equal to what? The S upper O T2 minus T1. Okay? So that the equation, this equation here, becomes what? Becomes this one over here. Okay, so basically this is the equation. I just wanted to rewrite on, say, recalling the equation. So we did this, no? Okay, I thought we did it, so it's good. It's just a review. So let me go back then. To this page over here. That will be now 110. So let's say recalling, so we just have to do the equation delta S equals Cp dt over T minus R log P2 over P1 will also be equal to what? Okay, so now what do we need to do? So from where are we going to get these values over here? Table A22. So let's say table A22, what do we have? T1 equals to 27 degrees Celsius. So we're going to find here the S sub O. T2 equal to 207 degrees Celsius. So the S sub O will be another value. So why is this crook over here? No, this is better. So if we go now to the tables, A22 I think was page 1030 or close to that. No. A22. now I went too far. Okay, maybe I should not do this. 1000, let's see what we get here, 815. We need to go to 822. Oh, so I think it was 963.
These are all English.
Yeah,
963.
963. So 822, we have temperatures in what over here? Temperature in Kelvin. So okay, so all right, so before that, 27 degree Celsius will be how many Kelvin? So this will be 300 Kelvin, and 207 will be 480. Kelvin. So if we look now at the tables, 300, 480. So for 300, what is that S sub O here is 1.7. Seven 0203, and the T2 for 480 here it is, will be 2.1 7 7 60. So I'm just looking at the units, will be kilojoules, kilogram Kelvin, so kilojoules, kilogram Kelvin. All right, and okay, what else do we need over here? What is R? R is the ideal gas constant, which is equal to what from your table? 8.314 kilojoules per kilomole Kelvin. All right, so if we do the substitution, so numerical application, delta S so what do we get over here? We're gonna get, I'll do it in black, it's newer, I'm running out of so we're gonna get 2.1776 minus 1.70203 minus 8.314 Okay, we need to be careful here because what will be R? You see my mistake here. Yeah, because R is R bar over the molar mass, and the 8.314 is R bar. Yeah, the gas constant is R bar. Okay, and R is the gas constant. So the air, what is the gas? The air, no? So we need to divide the gas constant by the molar mass of the air. So we have this over here, so this will be divided by 28.97. This will be coming from what table? Table 1, no? Yeah? I mean, by now, I don't do all the steps, okay? So now, log, do we know P2 and P1? So P2 is 0.5, the units are okay, and this is 0.1, so basically is 5. So how much do you get? Wait, I can have here a value, I think. What do you get?
0.0137.
Yeah, that's what I have here. And the units will be kilojoules per kilogram Kelvin. Okay, so I'm going to write down one more equation, and then let's see if you can give me the answer. So 111 okay, so principle of increasing entropy says what? I'm not going to redo it again. The derivation is higher or equal to 0. Okay? So if you don't understand this, let me know, okay? But basically, we had the principle of increasing entropy was really that, let me do one line. The change of entropy of the surrounding plus the change of entropy of the system since the entropy, since almost everything that happens on Earth is what? Irreversible, no? So if it's irreversible, what does that mean? That is, the entropy is positive, and you're putting entropy into the universe, no? Into the surrounding. So we say the entropy will always be positive, increasing. Okay. So now this equation involves what? The total change of entropy is equal to the heat plus the change of entropy of the system. No. Okay. So in this problem, which value did we calculate it? We calculated this one to be 0.0137, no? Okay? So now, that's the only way I know how to do this problem if you ask me. So now, since our delta S equal to 0.0137, it's already higher than 0. Okay, I say higher or equal than 0. can this process happen without any Q? Yes or no? So we could do it without the Q, no? Okay. So what are the question? What was the question over here? Oh, now we need to go to. Now I forgot the page number. Was 363, no? Almost, but we'll go down this way. Was 650. So what was the question over here? Okay, so if the process can happen adiabatically, if yes, determine the work in appropriate units. So can this process happen adiabatically? Yes, no? We don't need Q for this process to happen. So Q in this process or if you want, delta Q can be 0. So yes, it can happen adiabatically. So if it happens adiabatically, they ask us to calculate the work. Again, I'm doing this problem, but to be honest with you, I don't like it, okay? I don't think this is easy. So, if you want to calculate the work, what would be the work equal to? So for the closed system, what will you have? You have Q plus work would be equal to what? Change in internal energy, no? Okay? So if we neglect the kinetic potential energy and so on, what are you going to get? So in this case, what is Q? This is adiabatic. This is 0. So this will give us that work over mass. We have the mass over here? No, work over mass will be equal to what? U2 minus U1. So from where do we get U2 and U1? So I guess it's table 822 again. So what were the temperatures? I think we just did it. So T1 equals, but let me put it 27 degrees Celsius, 300 Kelvin. T2 equals to 207 Celsius, which will be 480 Kelvin. What will be the values for U1 and U2? Oh, here we go. What was the page? Remember 9? Okay. '21, '22. So let's see, at 300, U is 214.07. And at 480 is 344.7. So what would be the work? Would be equal to 344 0.7 minus 214.07. What would that give you? 130.63, no? Kilojoules per kilogram. Okay, so now what are we gonna do for case 2? We're gonna follow exactly the same process and we'll see what happens. So what happens now if the delta S is negative? I mean, I hope this is what's gonna happen, no? So then the delta Q cannot be 0, no? So we need to find what should be the value of the Q or the direction of the Q. I don't know. So case 2, and let's go back to the initial page, which was 360? 350, no? I don't know, I keep remembering. Oh, 350, now I got it right. So case 2, we got P1 equal to 3 atmospheres. Why do they change this stuff? T1, 80 degrees Fahrenheit. P2, 10 atmospheres. Oh, and they say to use T. Okay. T2 equal to 240. And this time, instead of using the table, they say to use Cp equal to 0.241. So we're going to do it both ways so that you see if there is any difference. This is the way I will do it, okay? I don't like the tables, to be honest with you. I know they are more accurate, but I don't care that much about the tables. So 960. No, now we go English units. So let's say 1000, see what happens. So we need 822E, I'm guessing, if we want to use it. But we might use it or not use it. We'll see what happens. Okay. All right, so first here they give us the temperature in Rankine. So we need to change that stuff then. So how many Rankines will be 80? I can live with 540, okay? 540, and then the 240 will be 700. Okay, so here we have two ways to do this, okay? So let's say assuming Cp constant, which is what they're asking us to do basically, what is delta S equal to? Will be equal to what? Cp log T2 over T1 minus R log P2 over P1. Okay? But let's say Cp is in function of the temperature. So in that case, what will be delta S? What we just did before, no? Yeah? So obviously they don't ask you to do it both ways, but let's see what is the difference. Okay? Alright, so let's first do it using this one. So 111. Oops, I broke the page. Big deal. So $112, we will use delta S equals to Cp log T2 over T1 minus R log P2 over P1. What do we get? I don't want to use the blue, it's short. 0.241 times log, what was T2 that we calculated? 700 divided by 540. Minus, I mean, you need, I don't know those values, so what is the R in English units? R bar, sorry, what is R bar in English units? 9 point? 1.986. And the units for that, it doesn't matter, but okay, so the same ones? Okay, good. Log. Can we use atmospheres in English units? Yeah, it doesn't matter because the ratio should be the same. Yeah, it should be the same. So, what were the pressures? 10? 10 over 3. Yeah, as long as the units are the same, the ratio should be the same, no? So what do you get for delta S? Doing it that way, I think I might have the result for that one. Yeah, that's the way they did it here. So they get a negative value. Is that what you get? That's good. So negative 0 point, they get negative 0.02. Is that what you get?
Yes.
Okay. Exactly the same value? Okay, so that's why I'm saying why to use the tables, no? Personally, I'd rather do this than to use tables, okay? Okay, or using table, delta S should be equal to what? S sub O T2 minus S sub O T1 minus R log P2 over P1. So I'm guessing that from table A22E at T1 equals to, what do they give the temperatures on? Is it Rankine? Yeah, that's why we change it. So at T1 equals to 540. And T2 equal to 700 Rankines. We get the entropy S upper O, so 540, 700. So 540 will be 0.60078. If you want, I'll highlight it here on the table. And for 700, 0.66321. Okay? And the other value should be the same. So delta S would be equal to what? 0.66321 minus 0.60078 minus 1.986 divided by 28.97 log of 10 over 3. So please check. Let's see if you get something similar. So do you get 0.02? Exactly the same thing? Okay, so like I told you before, guys, to tell the truth, when personally, it's not that it happens often, but if I need to do a program of thermodynamics and I can just go to the CP value and not use the tables, is what I do, okay? I don't like that S upper O, you know? Because I think you lose physical meaning. I get lost. As soon as you go too much to the tables, I think you lose a lot of physical meaning. Okay? But basically it's good. You see, you can use either one, no? Yeah? So now, so let's do the same thing. So from principle of increase in entropy, which is what? Minus delta Q over T plus delta S needs to be higher or equal to 0. So this one we calculate to be equal to minus 0.02. So if the process must happen, in that case, can Q be 0? No, it must be a Q, no? Okay? And actually the whole term should be what? Positive. Okay? So for process to occur, minus delta Q over T needs to be positive. Okay? So what was the question they were asking us? Then in what direction the Q needed to be? So to know what is the direction of the heat transfer? Okay, so if this is, what was our system? Was there was the pistons in the assembly? So should the Q be coming inside the system or out of the system? If it goes inside, it's positive. If it goes outside, the Q is negative. We need to have a negative Q, no? So you have negative, negative. Yeah? So what do we need to say here? So the Q, let's say they say here. No. So the Q, here they say from the system to the surrounding. So the Q is what? Is going out of the system. Did you understand the process of this problem? Okay. Again, this is like watching sport on TV. When I do it, it's yes, yes, but then that wasn't easy, okay, to tell the truth. I think that one was a little bit tricky. So it's not a kind of problem that I will, if you haven't done it before, probably I would never give you this problem on an exam. Because it's a little bit of hit or miss, no? If you know the equation and it's not really going through any process. So maybe, okay, we did it. I think you learned something, so it's good. So which problem you want to do next then? Let's see if we have time to do another one. 664. Let me look at this one a little bit more detail because this one was good, but not that good. I mean, 664, I don't mind doing it, but we did one in class very similar, no? So 664 is the one, I mean, I'll show you here. Basically, I haven't looked at too much of the problem, but it looks to me like you have different air at different temperatures, no? And different pressure. So what's gonna happen when you combine those two airs at different temperature and pressure? You're gonna get a different pressure and different temperature, no? So how do you find, I mean, I'm guessing that's the problem. So how do you find the final temperature? Remember, you do this, the delta U, I'll show you here. Let's do it this way, okay? You find, you will say that the total delta U will be 0, no? Okay? The delta U is equal to the change of entropy of the first gas plus the change of internal energy of the second one. So you know the initial temperatures, you can find the final temperature, that will be the final temperature of the mixture of this air with this air. I mean, here was it a big mystery? If it's 400 and 400, what should be the final? Hopefully they get 400, no? Yeah? See, a lot of math for nothing. But now, the total volume, what's going to be the total volume? 3, no? But we need to find what will be the final pressure. So in order to find the final pressure, what do? They do, this is for the P final, but the mass will be the final one, no? So what happens is that you need to first find from the PV equal nRT relation, you need to find what is the mass. You know P, you know V, you know T. Can you find the mass?
Yes.
Do you know P, V, and T? Can you find the mass over here? Yes, no? So once you have the masses, the total volume, you substitute into this equation and voila, no? You follow the process? It's not that I don't want to do it, but I'd rather try to do something else, okay? I think we did something similar to this one. And then the total change of entropy at the end will be equal to what? The change of entropy of this part over here of the system plus the change of entropy of this one, no? So what is the initial temperature here? 400, 400. So are the temperature going to give you anything? Oh, here it uses the gas relation. But you should do it also with the CP. You could do it, no? Okay? So it really should only be only these terms. Because this one should be 0. Because why is this term 0? The same temperature, no? Same delta S because the same temperature. So it should only be about the R's over here. And the R's is what is called the compressibility factor. So then that's it. You just substitute for the R's and you find the total change of entropy is 0.1274. Alright, it's not that I don't want to do it, but I'd rather do something else. What else? Which problem you want to do? Chapter 5, 10, okay. You want to move, we can change chapters. Didn't we do that one or something similar? Let's do that one, okay. 5, 10. I already do these ones because I know these ones are more like symbolic. And so let's see what is that one. Okay, let's do that one. All right. Page 113. Five ten. that was very quick. Five, 10. These problems, guys, I do this one because they're always the same, but it's not the type of problems you are used to. So which one is it? 5, 9. This one, okay. So basically, just look at the figure. So let me read the problem. Shows two power cycles denoted 1 and 2 operating in series together with 3 thermal reservoirs. The energy transferred by each transfer is equal to the magnitude of each transfer by each. Okay, so it's Q. All right, so let's do the figure. Copy exactly that figure if you want to do it a bit different. So TH, T, TC. And everything is Q. Okay, I got it. I think I got that one. So over here looks like we have a hot reservoir at TH that go to the first power cycle, and I'm guessing this will be QH, and then this one remove Q. So let's say this is 1, and now this goes into 2. And now, no, I got lost. Let me go back to the figure. Oh, I forgot to do the reservoir in the middle. Okay, yeah, now I get it. So, all right, so we have a reservoir. All right, I'm gonna restart from 0. $113, so we have 510. We have 1 hot, one cold, and let's say we have 1 at a temperature T. So here we have our first power cycle, which I guess is giving heat QH. Okay, they're all called Qs. Okay. So QH. Then this one here will be QC, and in the middle is just Q and Q, and these two are power cycles. Yeah. Okay. I don't have to remove the figure, let me just read. Determine an expression for the thermal efficiency of an overall cycle consisting of cycles 1 and 2 and express in terms of their individual thermal efficiencies. So determine an expression for the thermal efficiency of the overall cycle. Okay, I think I got it. So part A, overall efficiency in function of each of the efficiency of each engine, so will be eta 1 and eta 2. Oops. Okay, so the way I will solve this problem is this way. What are we trying to find? What is the efficiency of the overall cycle? So what is the efficiency for a power cycle? Is whatever we get out divided by whatever we put in. So what do we get out? So what would be the work then? Work 1 plus work 2, no? Okay? And what do we put in? QH. Okay, so let's try to simplify this a little bit more. What would be the work of the first power cycle? QH minus Q, no? Yes? If you have questions, this is the time. What would be the work done by the second one? Q minus QC. Divided by QH. So this will give you what? The Q's will cancel out. QH minus QC over QH, or 1 minus minus Q cold over Q hot. So really that expression, what is it telling you? Something that we already knew, but let's just repeat it. Is that we don't care about what's happening inside, because this could be your engine, no? Let's say you could have two engines in the middle, no? At the end of the day, what is the most important thing? Is the total difference in temperature, okay, between the hot and the cold reservoir. Okay, so now we have the efficiency in function of what? Of the QC and the Q hot. Those are not easy to measure. So they want us to find the same expression, but in function of what? The efficiency of the first one and the efficiency of the second one, no? So if we write down the efficiency for, let's say, for the first engine, what would be the expression? What is the efficiency for 1? Would be work 1 divided by Q hot. So do we know something about the work? Do they tell us something about the work? Are they different or are they the same? Okay, so I don't know what to do with that work 1, so let's try to eliminate it. What would be the work 1 equal to? I mean, we just did it before. It's QH minus Q over QH. So this will be equal to what then? 1 minus Q over QH. Okay, so I think I know what's gonna happen. So I mean, maybe we should not put it that way, but okay, so we have the expression. Let me just rewrite it. I don't want to do the algebra without showing to you. So we have 1 minus q over qh. So from this one, what are you gonna have? So alright, so I do step by step. We have q over qh. So I'm moving q over qh to the other side, and I'm leaving this one on this side. So this will be equal to what? 1 minus the efficiency of 1, no? So qh will become what? Q divided by 1 minus the efficiency of 1. Okay, let's see if we have time to finish this part. I mean, guys, you see what I'm trying to do? All right, so now what do I need to do for the second one? What will be the efficiency of the second one? Work 2 divided by what? Q. So, all right, so Q. So what is work 2 will be equal to what? Q minus Q cold over Q, no? So this is equal to 1 minus Q cold over Q, which will mean that Q cold over Q equal to 1 minus the efficiency of the second one, or Q cold equal to Q times 1 minus the efficiency of the second one. So now, what am I going to do? I come back to this one, and you see it doesn't matter that I have the Q because one is dividing the other one, no? So what's going to happen to the Q's? They should cancel each other, no? All right, that was the whole idea. So 114. So substituting so Romans 1 and 2 into A, what do we get? One minus so QC is equal to Q times 1 minus the efficiency of the second one, and Q hot is equal to Q divided by 1 minus the efficiency of the first one. So the heats are going to cancel out, and the total efficiency is going to be equal to 1 minus which, I mean, you can leave it this way, or if we do the algebra, this would be equal to what? 1 minus what? 1 minus eta 1 minus eta 2 plus eta 1 eta 2. So the ones are going to cancel out, and the total efficiency is equal to the efficiency of the first one plus the efficiency of the second one minus the product of the efficiency of each one of them. Okay, guys, I'm not gonna do the second part because it's time, but I hope you are doing the homeworks because homeworks is the time for you to practice, no? All right. So one more thing, we're getting close to the end of the semester, and I don't go and check if you uploaded all your work, but please upload all your homeworks and exams 1 and 2. It's not that I want to check on you, it's because next year the whole College of Engineering is going through accreditation, and sometimes some of the courses get audits, okay? So they want to see some of the material. So it's for your own good, okay? It's not that I want to check on you or anything like that.